Welcome to a journey beyond the limits of imagination. Out there in the vast darkness of the universe, there are objects so large, so extreme, that even our best understanding of physics begins to struggle. We've discovered stars that dwarf our sun, stars so massive they could swallow entire solar systems without effort. But among all of them, there is a growing mystery, a possibility that somewhere in the cosmos there exists something even bigger, a star so enormous it shouldn't exist at all. Some astronomers have begun to refer to it as a behemoth, not because it has an official name, not because it has been fully confirmed, but because the idea itself demands a word that feels almost mythical, something that represents scale beyond reason. Something that forces us to ask a simple but unsettling question. What is the largest star in the universe? And more importantly, have we already found it? At first, this might seem like a straightforward question. After all, we measure stars all the time. We calculate their size, their mass, their brightness, their distance. We've mapped galaxies, observed black holes, and even detected gravitational waves from collisions billions of light years away. But when it comes to the largest stars, things become far less certain. Because size, in space, is not always what it seems. A star can appear enormous simply because of how its outer layers expand. Another may be more massive, but more compact. Some stars are constantly changing, swelling and shrinking over time. Others lose material so rapidly that their true size becomes difficult to define. So when we ask what the largest star is, we are not just asking for a number. We are asking how we define size itself. And that is where the mystery begins. Our own sun, for example, feels unimaginably large when compared to Earth. It is so big that over 1 million Earths could fit inside it. Its gravity controls the entire solar system. Its energy sustains life on our planet. And yet, in the grand scale of the universe, the sun is not special. It is average. There are stars hundreds, even thousands of times larger. Stars so vast that if they replaced the sun, their outer edges would stretch beyond the orbit of planets we know. Mercury, Venus, Earth, all of them would be swallowed without a trace. And still, even those stars might not be the largest. Because somewhere beyond the limits of easy observation, there may exist something even more extreme, something we are only beginning to understand, something we are not even sure we are measuring correctly. This is where the idea of the behemoth begins to take shape. It is not just a single star. It is a concept, a possibility, a question that sits at the edge of our knowledge and asks how far nature can really go. How big can a star become before it collapses under its own weight, before it tears itself apart, before the laws of physics simply refuse to allow it? These are not simple questions, because stars are not static objects. They are dynamic, unstable, constantly changing systems. Their size depends on a balance between gravity pulling inward and energy pushing outward. As stars grow larger, this balance becomes more fragile. The more massive they are, the more unstable they become. At some point, increasing size does not make a star stronger. It makes it weaker, more chaotic, more temporary. And yet, we continue to find stars that push these limits. Each discovery forces us to rethink what is possible. Each measurement introduces new uncertainty. Because the truth is, we cannot simply travel to these stars and measure them directly. We rely on light that has traveled for thousands, sometimes millions of years. We interpret that light, analyze it, and build models based on what we believe is happening. But light can deceive. Distance can distort. And our models, no matter how advanced, are still approximations. This means that when we identify a candidate for the largest star, we are often dealing with estimates, educated guesses. And sometimes, those guesses change. A star once thought to be the largest may later be revised to a smaller size. Another, barely noticed before, might suddenly appear far larger than expected. The ranking is not fixed. It is constantly shifting. And that is what makes the idea of the behemoth so compelling. Because it suggests that somewhere out there, beyond our current measurements, there may be a star that truly represents the upper limit. Or perhaps something that exceeds it. To understand how extraordinary this would be, we need to think about what size really means for a star. Unlike solid objects, stars do not have a clearly defined surface. Their outer layers are made of gas, gradually fading into space. This makes it difficult to determine exactly where a star ends. Different methods of measurement can produce different results. Whilst one method might define the edge based on temperature, another based on brightness, another based on density. Each approach gives us a slightly different answer. So when we say a star is the largest, we are choosing one definition over another. And that choice matters. Because in some cases, the difference is enormous. A star could appear twice as large depending on how you measure it. Now imagine applying that uncertainty to something already beyond comprehension. A star so large that even small measurement differences translate into distances greater than the orbit of planets. This is the scale we are dealing with. But there is another layer to this mystery. Even if we could measure these stars perfectly, there is still the question of whether such extreme objects should exist at all. Physics places limits on how stars behave. Gravity pulls matter inward, trying to compress the star. Energy from nuclear fusion pushes outward, trying to expand it. This balance determines the size and stability of a star. But as stars grow larger, their internal processes become more violent. Radiation pressure increases, instabilities form. Mass begins to escape into space. At extreme sizes, stars can become so unstable that they shed enormous amounts of material, preventing them from growing any larger. In some cases, they may even collapse or explode. This suggests that there is a natural limit, a maximum size that stars can reach before they become unsustainable. And yet, the candidates for the largest stars seem to approach and sometimes challenge that limit. Which brings us back to the central question. Have we already found the largest star? Or are we still underestimating what the universe is capable of? The idea of the behemoth forces us to confront that uncertainty. It represents the possibility that the universe is not done surprising us. That beyond our current observations, there may be stars larger than anything we have confirmed. Or that what we believe to be the largest may not actually hold that title. Because in a universe this vast, our perspective is always incomplete. We see only a fraction of what exists. We measure only what we can detect. And we understand only what our theories allow. Everything else remains hidden. Waiting. In the chapters ahead, we are going to explore this mystery step by step. These talks, we will begin by understanding how stars form and what determines their size. We will look at the largest stars we already know and compare their scale to everything familiar. We will examine the candidate known as the behemoth and question whether it truly deserves that title. And along the way, we will confront a deeper truth. That the question of the largest star may not have a final answer. Because the universe is not static. It is expanding, evolving, constantly revealing new extremes. Which means that somewhere, at this very moment, there could be something larger. Something we have not yet seen. To understand whether something like a behemoth can truly exist, we first need to answer a much more fundamental question. How big can a star actually get? At first, it might seem like there should be no limit. After all, stars are made of gas, and gas can expand outward into space without any solid boundary. But in reality, stars are governed by a delicate balance of forces, and that balance places strict limits on how large they can become. Every star begins its life inside a massive cloud of gas and dust. These clouds, often spanning light years across, slowly collapse under their own gravity. As the material falls inward, it becomes denser and hotter, eventually forming a central core where temperatures rise high enough to ignite nuclear fusion. This marks the birth of a star. From that moment on, the star is defined by a constant struggle between two opposing forces. Gravity pulls everything inward, trying to compress the star into a smaller and denser object. At the same time, nuclear fusion in the core releases enormous amounts of energy, creating pressure that pushes outward. When these two forces are balanced, the star remains stable. This state, known as hydrostatic equilibrium, determines not only the star's structure, but also its size. For smaller stars, this balance is relatively stable. Gravity is weaker, and the energy produced by fusion is moderate. These stars can exist for billions of years without dramatic changes. But as stars become more massive, everything begins to intensify. The core becomes hotter, fusion reactions accelerate, and the amount of energy pushing outward increases dramatically. At first, this allows the star to grow larger. More energy means more outward pressure, which expands the outer layers. This is why massive stars are often much larger than smaller ones. But this growth cannot continue indefinitely. As a star increases in mass, the energy it produces rises at an even faster rate. This creates a new problem. The outward pressure from radiation becomes so strong that it begins to counteract gravity in a different way. Instead of simply balancing gravity, it starts pushing material away from the star entirely. This is where the concept of a natural size limit begins to emerge. There is a point at which adding more mass to a star does not make it larger in a stable way. Instead, it makes the star more unstable. The intense radiation pressure drives powerful stellar winds, streams of particles that are blown off the surface at incredible speeds. These winds carry away mass, effectively preventing the star from growing any further. In other words, the star begins to lose material as fast as it gains it. This creates a kind of upper boundary. Even if a star forms from a very large cloud of gas, it cannot simply continue growing forever. The forces within it push back against further expansion, enforcing a limit on both its mass and its size. But size and mass are not always directly linked in the way we might expect. A star's size is not determined only by how much matter it contains. It also depends on how that matter is distributed and how energy moves through the star. Some stars are incredibly massive, but relatively compact. Others are less massive, but have outer layers that expand to enormous distances. This is especially true for the largest stars we observe, known as red supergiants and hypergiants. These stars have reached a stage in their evolution where their outer layers expand dramatically, creating sizes that are almost impossible to visualize. Their surfaces extend far into space, becoming diffuse and loosely bound compared to the dense cores within. This expansion happens because of changes in the star's internal structure. As fusion processes evolve, energy is transported outward in different ways, causing the outer layers to swell. The result is a star that can be hundreds or even thousands of times larger than the Sun in radius, even if its mass is not proportionally greater. But this expansion comes at a cost. The larger a star becomes, the weaker its grip on its outer layers. Gravity decreases with distance, and at extreme sizes, the outer regions are only loosely held in place. This makes them highly unstable. Pulsations can occur, causing the star to expand and contract over time. Massive amounts of material can be ejected into space, forming clouds of gas that drift away from the star. These processes limit how large the star can remain. Even if it briefly reaches an enormous size, it may not be able to sustain that size for long. It may shrink again or lose enough material to reduce its overall scale. This means that the largest star is not always a fixed title. It can change depending on when and how the star is observed. Another factor that complicates things is the definition of a star's boundary. Unlike a planet which has a solid surface, a star gradually fades into space. Its outer layers become less dense and less defined as you move away from the core. This makes it difficult to determine exactly where the star ends. Different measurement techniques can produce different estimates of its size, especially for stars with very extended atmospheres. This uncertainty becomes more significant as stars grow larger. For extremely large stars, small differences in measurement can translate into enormous differences in size. What one method defines as the edge of the star, another might consider part of its surrounding environment. This makes it challenging to compare stars directly and declare one definitively larger than another. So when we ask how big a star can get, we are not just asking about physics. We are also asking about how we measure and interpret what we observe. Despite these challenges, there are theoretical limits. Astrophysicists have proposed upper bounds on stellar mass, often around a few hundred times the mass of the Sun. Beyond this, the effects of radiation pressure become so strong that the star cannot remain stable. It sheds mass rapidly, preventing further growth. These limits are not exact, but they provide a framework for understanding what is possible. For size, the limits are even more complex. A star could, in theory, expand to an enormous radius if its outer layers are diffuse enough. But maintaining such a structure becomes increasingly difficult. Instabilities grow, mass loss increases, and the star's lifespan in that state becomes very short. This means that the largest stars we observe are often in a temporary phase. They are not stable giants that will remain unchanged for millions of years. They are evolving, fluctuating, and often nearing the end of their life cycles. Their enormous size is part of a process that will eventually lead to collapse, explosion, or transformation into something else. This brings us back to the idea of the behemoth. If there is a star that represents the upper limit of size, it would likely exist in this unstable, short-lived state. It would be difficult to observe, difficult to measure, and constantly changing. Its size might vary over time, making it hard to determine whether it truly holds the record. And even if we identify such a star, there is always the possibility that something larger exists elsewhere, beyond our current reach. Because the universe is vast, far larger than what we can observe directly. There are regions of space so distant that their light has not yet reached us. There are stars hidden behind clouds of dust, invisible to our instruments. There are galaxies we have not fully explored, each containing billions of stars. Within that vastness, the idea of a single largest star becomes uncertain. It is not just a matter of finding it. It is a matter of whether we can ever be sure we have. This uncertainty is what makes the search so compelling, because it is not just about identifying a record. It is about understanding the limits of nature itself, and whether those limits are fixed or still waiting to be discovered. Before we can understand the idea of a true cosmic behemoth, we need to explore the giants that already exist. Because the universe is not short on massive stars. In fact, some of the largest stars ever discovered already push the limits of what we once believed was possible. And yet, even among these extremes, there is still uncertainty, still debate, and still the possibility that something even larger is waiting to be found. Our journey begins with a simple comparison. The Sun, the center of our solar system, feels enormous when viewed from Earth. It dominates our sky, controls the motion of planets, and provides the energy that sustains life. But in the broader universe, the Sun is not a giant. It is a relatively average star, both in size and mass. Now imagine something much larger. Not 10 times larger, not even 100 times larger. But a star so vast that if it replaced the Sun, its outer layers would stretch far beyond the orbit of Earth. A star so large that entire planetary systems could exist within its atmosphere. These stars exist. They are known as red supergiants and hypergiants, and they represent some of the most extreme forms of stellar evolution. These stars are not only massive, but they have expanded to incredible sizes as they approach the later stages of their lives. One of the most well-known examples is a star located in the constellation Scutum. It's often cited as one of the largest stars ever measured. Its radius is estimated to be more than 1,000 times that of the Sun. If placed at the center of our solar system, it would extend beyond the orbit of Jupiter, engulfing Mercury, Venus, Earth, Mars, and even the asteroid belt. This is not an exaggeration. It is a real measurement based on observations and models. And yet, even this star may not hold the record, because there are others. Stars that rival its size, challenge its measurements, and sometimes exceed it depending on how they are observed. Another example lies in the constellation Canis Major, a star often mentioned in discussions of the largest known stars. Its estimated radius is so vast that it pushes the boundaries of what we thought stars could reach. But like many of these giants, its exact size is uncertain. Different methods of observation can produce different results, leading to ongoing debate about its true scale. This uncertainty is not a flaw in science. It is a reflection of the difficulty of measuring objects at such extreme distances. These stars are thousands of light years away. We cannot see them as solid objects. We detect their light, analyze their spectra, and use that information to infer their properties. The process is complex, and small errors can lead to large differences in the final estimates. But even with these uncertainties, one thing is clear. These stars are enormous beyond comprehension. To better understand their scale, consider this. If you were to travel at the speed of a modern jet aircraft, it would take you more than 1,000 years to circle the Sun once. Now imagine a star 1,000 times larger in radius. The journey would become so vast that it would no longer feel like traveling around a star, but across a world. And yet, these stars are not solid. They are made of gas. Their outer layers are diffuse, extended, and constantly shifting. The boundary between the star and the surrounding space is not sharp, but gradual. This makes their size even more difficult to define. Some regions are dense enough to be considered part of the star, while others blend into the surrounding environment. Depending on where you draw the line, the size of the star can change significantly. This is one of the reasons why the title of largest star is so difficult to assign, because it depends on how you measure it. There is also another important factor to consider: mass. While these giant stars are incredibly large in size, they are not always the most massive. In fact, some of the most massive stars in the universe are much smaller in radius, but contain far more matter. These stars burn hotter and brighter, producing enormous amounts of energy. But because of that energy, they do not expand in the same way. Instead, they remain relatively compact. This highlights an important distinction. Size and mass are not the same. A star can be enormous in size, but relatively low in density, with its outer layers spread out over vast distances. Another star can be much smaller, but far denser and more massive. When we talk about the largest star, we are usually referring to size, not mass. And that distinction matters, because it means that the largest stars are not necessarily the most powerful. They are simply the most extended. These giant stars are also unstable. Their size is not permanent. They expand and contract over time, sometimes dramatically. Pulsations can cause their outer layers to move in and out, changing their radius over periods ranging from months to years. This means that a star measured at one time may appear larger or smaller when observed later. In some cases, the changes are extreme. A star might swell to an enormous size, only to shrink again as it loses energy or material. This dynamic behavior adds another layer of complexity to measuring and comparing these objects. It also raises an important question. When is a star at its true size? At its largest point, its average size, or some other definition entirely? There is no simple answer. Mass loss is another defining characteristic of these giants. Because their outer layers are so loosely bound, they are constantly shedding material into space. Stellar winds carry gas away at high speeds, creating vast clouds of matter surrounding the star. Over time, this process can significantly reduce the star's mass and alter its structure. In some cases, the mass loss is so intense that it shapes the star's evolution, determining how it will end its life. These stars are often nearing the final stages of their existence, preparing for a dramatic collapse or explosion. This means that the largest stars we observe are often temporary giants. They exist in a brief phase of expansion before transitioning into something else. A supernova, a neutron star, or perhaps even a black hole. Despite all of this, the search for the largest star continues. Astronomers scan the skies, analyze data, and refine their models, looking for candidates that push the limits even further. Each new discovery adds to the list of extreme stars, each one challenging our understanding of what is possible. And yet, there is always uncertainty, because for every star we identify, there may be others we have not yet seen. Stars hidden behind interstellar dust, invisible to certain wavelengths of light. Stars located in distant galaxies, too far away for precise measurement. Stars that are simply too rare or too short-lived to be easily observed. The universe is vast, and our view of it is incomplete. This means that the list of the largest known stars is not final. It is a snapshot, a moment in time. And this is where the idea of the behemoth becomes even more intriguing. Because if the largest stars we know already challenge our limits, then the possibility of something even larger becomes both exciting and unsettling. Is there a star out there that dwarfs all of these giants? A star that exceeds every known measurement? Or are we already close to the maximum, with these giants representing the upper boundary of what is possible? At this point, we do not know. But the candidates we have seen suggest that the universe is capable of producing objects far beyond what we once imagined. And that means the search is far from over. After exploring the largest stars we already know, a pattern begins to emerge. The universe is capable of creating objects so vast that they stretch the limits of our understanding. Yet, every time we think we've reached the boundary, something new challenges that assumption. This is where the idea of the behemoth begins to take form, not as a confirmed object, but as a possibility that refuses to be ignored. The term behemoth is not an official scientific name. It is not listed in catalogs or assigned to a single confirmed star. Instead, it represents something larger than a specific object. It is a way of describing a category of stars that may exist at the extreme edge of what is physically possible. A label for something so massive, so extended, that it forces scientists to question whether their current models are complete. But this idea does not come from imagination alone. It comes from observation. Over time, astronomers have identified stars whose estimated sizes push far beyond expectations. Some of these stars appear to rival or even exceed the largest known red hypergiants. Their outer layers extend to distances that seem almost impossible to sustain. And yet, the data suggests they are real. At first, these observations were met with caution. When a star appears unusually large, the first assumption is often that something in the measurement is off. Perhaps the distance is miscalculated. Perhaps the light we observe is affected by surrounding dust or gas. Perhaps what we are seeing is not a single star, but a combination of multiple sources blending together. These are reasonable concerns, because measuring something this distant and diffuse is incredibly difficult. But in some cases, even after accounting for these uncertainties, the numbers remain extreme. Stars that should not be that large appear to be exactly that. And this is where the concept of the behemoth gains strength. It is not based on a single discovery, but on a growing pattern. A pattern suggesting that the upper limits of stellar size may be higher than we once believed. That the universe might be capable of forming stars that exist right at the edge of stability, or even beyond what our current theories predict. One of the most intriguing aspects of these potential behemoths is how they challenge our understanding of stellar structure. According to established models, stars cannot grow indefinitely. As we discussed earlier, increasing size leads to increasing instability. Radiation pressure pushes outward, stellar winds strip away mass, and the outer layers become too loosely bound to remain intact. In theory, this should create a natural cap, a maximum size that stars cannot exceed. And yet, some observations seem to approach or even surpass this limit. This does not necessarily mean the theories are wrong, but it does suggest that they may be incomplete. There may be factors we do not fully understand, conditions under which stars can temporarily exceed expected limits, or mechanisms that allow them to maintain stability for longer than predicted. These possibilities open the door to something new. Not just larger stars, but new types of stellar behavior. Another reason the behemoth concept is so compelling is the scale involved. We are not talking about a small increase in size. We are talking about differences so large that they redefine what it means for a star to be big. Imagine a star that is not just larger than the known giants, but significantly larger. A star whose radius extends so far that it would engulf not only the inner planets of a solar system, but much of the outer regions as well. A star so vast that its surface would feel less like a boundary and more like a transition into space. A star whose outer layers are so diffuse that they blur the line between star and surrounding environment. This is the scale we are considering. And at this scale, even defining the object becomes difficult. Is it still a star in the traditional sense, or something else entirely? The idea of the behemoth also forces us to reconsider how we interpret data. When astronomers observe distant stars, they rely on light, its brightness, its spectrum, its variation over time. From this information, they estimate properties like temperature, composition, and size. But these estimates depend on models, and models depend on assumptions. If those assumptions are slightly off, the results can change significantly. For example, if a star is surrounded by a thick cloud of gas and dust, its light may appear more spread out than it actually is. This could make the star seem larger than it truly is. On the other hand, if certain features are not properly accounted for, the size could be underestimated. This means that when we identify a candidate for a behemoth, we must be cautious. Is it truly that large? Or are we seeing an illusion created by distance and environment? This question does not weaken the idea. It strengthens it, because it highlights how little we truly know. There is also the possibility that the largest stars are not stable objects at all. They may exist only briefly, in transitional phases that are difficult to observe. A star could expand rapidly, reaching an enormous size for a short period before shedding mass or collapsing inward again. If this is the case, then the true behemoth might be something we have only glimpsed momentarily. A star caught in a brief window of extreme expansion. A snapshot of something that does not last. This would make it even harder to identify and confirm. Because by the time we observe it again, it may have changed or disappeared entirely. Despite all these uncertainties, the search continues. Astronomers are constantly refining their techniques, using new instruments and methods to improve accuracy. Observations across different wavelengths, from visible light to infrared and beyond, allow them to see through dust and detect structures that were previously hidden. Each improvement brings us closer to understanding these extreme objects. And with each new discovery, the possibility of a true behemoth becomes more real. But perhaps the most important thing the behemoth represents is not a specific star, but a shift in perspective. It reminds us that the universe does not always conform to our expectations, that limits we consider fixed may only be temporary, that what we believe to be the largest, the most extreme, the most impossible, may simply be the edge of what we have seen so far. And beyond that edge, there may be more. When we talk about the largest stars in the universe, it is easy to imagine that astronomers simply observe them, measure their size, and record the result. But the reality is far more complex. Measuring something as distant and diffuse as a giant star is not a direct process. It is an act of interpretation, built on layers of observation, calculation, and assumption. And when the object in question is something as extreme as a potential behemoth, even the smallest uncertainty can become enormous. The first challenge begins with distance. Most of the largest stars we study are located thousands of light years away. This means the light we observe today left those stars thousands of years ago. We are not seeing them as they are now, but as they were in the distant past. Even determining how far away they are is a difficult task, requiring careful measurement of subtle shifts in their apparent position or brightness. If the distance estimate is even slightly off, the calculated size of the star changes dramatically. A star that appears to be the largest known could suddenly shrink or grow in our models, and simply because its distance was revised. This is the first layer of uncertainty. The second challenge is defining the edge of a star. Unlike planets, stars do not have a solid surface. Their outer layers gradually thin out, fading into space. This makes it difficult to determine where the star actually ends. Scientists must choose a point at which the density or brightness drops below a certain threshold and define that as the boundary. But this choice is not universal. Different methods can produce different results. One method might define the edge based on temperature, identifying where the star's outer layers cool to a specific level. Another might use brightness, marking the point where the light becomes too faint to distinguish from the surrounding space. Each approach leads to a different estimate of the star's radius. For smaller stars, the differences are manageable. For the largest stars, they can be enormous. A slight change in definition can add or subtract distances greater than the orbit of planets. The third challenge involves the star's environment. Many of the largest stars are surrounded by vast clouds of gas and dust. These clouds are often created by the star itself as it sheds material through powerful stellar winds. Over time, this material accumulates, forming an extended envelope around the star. When we observe such a star, we are not always seeing just the star itself. We may also be seeing the surrounding material. This can make the star appear larger than it truly is. The light we detect may be scattered or emitted by the surrounding gas, creating the illusion of a more extended structure. Distinguishing between the star and its environment becomes a major challenge. In some cases, what appears to be a single massive star could actually be a combination of the star and its surrounding cloud, or even multiple stars blending together in our line of sight. Another complication comes from variability. Many giant stars are not stable in size. They expand and contract over time, sometimes dramatically. These changes can occur over periods ranging from months to years. This means that a star measured at one moment may appear larger or smaller when observed later. For a star near the upper limits of size, this variability can be significant. It raises the question of which measurement represents the true size. Is it the maximum expansion, the average size over time, or something else entirely? But there is no simple answer. Modern astronomy uses advanced tools to address these challenges. Telescopes operating at different wavelengths allow scientists to observe stars in ways that were not possible before. Infrared observations, for example, can penetrate dust clouds, revealing structures that are hidden in visible light. Radio telescopes can detect emissions from gas and particles, providing additional information about the star's environment. Interferometry, a technique that combines signals from multiple telescopes, allows astronomers to achieve extremely high resolution. This makes it possible to measure the apparent size of distant stars with greater precision. But even these tools have limitations. They rely on models to interpret the data. And those models depend on assumptions about how stars behave. This brings us to one of the most important points. When we say a star is the largest known, we are not stating an absolute fact. We are presenting the best estimate based on current data and understanding, and that estimate can change. History has shown this repeatedly. Stars once believed to hold the record have later been revised to smaller sizes as measurements improved. Others, initially overlooked, have been re-evaluated and found to be larger than previously thought. This constant revision is not a weakness of science. It is a strength. It reflects a process of refinement, where knowledge becomes more accurate over time. But it also means that the idea of a definitive largest star is elusive. Even if we identify a candidate that appears to be the largest, we cannot be certain that something larger does not exist elsewhere. The universe is vast, and our observations cover only a fraction of it. There may be stars hidden from our view, or simply too distant to measure accurately. This uncertainty is at the heart of the behemoth concept. It suggests that the true upper limit may not yet be known, that what we consider the largest today may be surpassed tomorrow. There is also a deeper question. Are we even measuring the right thing? When a star becomes extremely large, its outer layers may become so diffuse that they are barely distinguishable from the surrounding space. At that point, the concept of a radius becomes less meaningful. The star does not have a clear boundary. It becomes more like a gradient, fading into the environment. In such cases, defining size becomes a matter of convention. We choose a point for practical reasons, but that point may not represent a physical boundary. This challenges the very idea of ranking stars by size, because the largest stars may not have a clearly defined edge at all. Despite these challenges, astronomers continue to push forward. New missions, more powerful telescopes, and improved techniques are constantly expanding our ability to observe the universe. Each advancement brings us closer to understanding these extreme objects. But it also reveals new complexities. The more we learn, the more we realize how much remains uncertain. So when we consider a potential behemoth, a star that may be larger than any we have confirmed, we must keep all of this in mind. Its size may be based on estimates. Its boundaries may be unclear. Its measurements may change. And yet, it may still represent something real. Something that pushes the limits of what stars can be. This tension between observation and uncertainty is what makes the search so compelling. Because it is not just about finding the biggest star. It is about understanding how the universe works at its most extreme, and whether our current models are enough to explain it. Up to this point, the idea of a behemoth has remained distant, abstract, almost impossible to visualize. We've talked about size in terms of numbers and comparisons, about limits and uncertainties, about stars so large they challenge physics itself. But to truly understand what such a star represents, we need to bring it closer. We need to place it somewhere familiar. So imagine for a moment that the behemoth exists, and not just somewhere far away, hidden in a distant galaxy, but here, at the center of our own solar system, replacing the sun. At first, nothing changes in your immediate surroundings. Earth is still Earth, the sky is still above you. But then you look up, and what you see is no longer the sun. It is something far larger, far closer, and far more overwhelming. The first thing you would notice is its size in the sky. The sun, as we see it now, appears as a small, bright disk, something you can block with your thumb at arm's length. But a behemoth would dominate the sky in a way that defies intuition. It would stretch across a vast portion of the horizon, not as a sharp-edged circle, but as a glowing, shifting presence that feels almost too large to comprehend. It would not look like a distant object. It would feel close, uncomfortably close, because the scale we are dealing with is beyond anything the human mind is designed to process. If this star is truly among the largest possible, its outer layers could extend beyond the orbit of Jupiter, or even further depending on how we define its boundary. That means Mercury, Venus, Earth, Mars, gone. Not destroyed in an explosion, not pushed away. Simply inside the star, swallowed by its atmosphere. The very idea challenges our sense of reality. Planets are supposed to orbit stars, not exist within them. But in this scenario, the inner solar system would no longer be a collection of separate worlds. It would be part of the star itself, embedded within its outer layers. Earth, if it existed at all, would not be a planet in the way we understand it. It would be exposed to extreme temperatures, intense radiation, and constant pressure from surrounding stellar material. The oceans would not boil. they would vanish. The atmosphere would not burn, it would be stripped away instantly. The surface itself would not remain solid for long. Everything would be transformed. But even this description barely captures the reality. Because the outer layers of a behemoth are not like the core of a star. They are diffuse, extended, and constantly moving. The density may be low compared to the interior, but the scale makes up for it. There is simply too much energy, too much motion, too much instability for anything to survive. It would not feel like being inside a solid object. It would feel like being inside a vast, turbulent ocean of plasma. An ocean that stretches for millions, even billions of kilometers. An ocean with no clear surface, no horizon, no escape. And yet, from a distance, this same star might appear strangely soft. Its edges would not be sharply defined. Instead, it would fade gradually into space, its outer layers blending into the surrounding darkness. This is one of the reasons measuring such stars is so difficult. Their boundaries are not clear. They are more like gradients than solid edges. So when we say that the behemoth could reach beyond Jupiter's orbit, we are speaking in approximations. The reality could be even more complex. Now consider the outer planets: Jupiter, Saturn, Uranus, Neptune. In our current solar system, these worlds orbit at vast distances from the Sun. But with a behemoth at the center, even these distances might not be enough. Depending on the size of the star, Jupiter itself could be engulfed, or at least skimming the outer layers. And its atmosphere would interact with the star's extended envelope, creating chaotic exchanges of energy and matter. The boundary between planet and star would blur, much like the boundary of the star itself. Saturn might exist just beyond the edge, orbiting through a region filled with stellar winds and intense radiation. Its rings would not remain intact. They would be disrupted, scattered, or absorbed. Further out, Uranus and Neptune might survive as distant observers, but even they would not be untouched. The radiation, the gravitational influence, and the changing structure of the star would alter their orbits and environments. The entire solar system would be transformed, not destroyed in a single event, but reshaped into something unrecognizable. There is also the question of gravity. A star as large as the behemoth does not necessarily have proportionally greater mass. As we discussed earlier, size and mass are not the same. The outer layers of such a star can be extremely diffuse, meaning that while its radius is enormous, its mass may only be tens of times greater than the Sun. But even that is enough to significantly alter the gravitational structure of the solar system. Orbits would shift, distances would change. The delicate balance that keeps planets in stable paths would be disrupted. Some objects might spiral inward, drawn closer to the star. Others might be pushed outward, escaping into deep space. The solar system, as a stable and predictable system, would no longer exist. It would become dynamic, chaotic, and unstable. And then there is the light. The sun provides a steady, consistent source of energy, and its brightness varies slightly over time. But for the most part, it is stable. A behemoth would be different. Its outer layers are often unstable, pulsating and shifting. This means its brightness could vary significantly. There could be periods of intense radiation followed by relative dimming. The light reaching any surviving planets would not be constant. It would flicker, change, pulse. This variability would make the environment even more unpredictable, not just in temperature, but in every aspect of energy distribution. But perhaps the most profound change would be psychological. Because even if you could somehow observe this system from a safe distance, Even if you were not affected by the heat or radiation, the sheer scale of the behemoth would alter your perception of reality. The sky would no longer feel like a distant dome, and it would feel dominated, occupied, filled by something so vast that it becomes impossible to ignore. The sense of space itself would change. Distances that once felt large would seem insignificant compared to the size of the star. The concept of a solar system would lose its meaning, because everything would revolve around something far more overwhelming than anything we have ever experienced. And yet, despite all of this, there is an important truth to remember. This scenario, as extreme as it is, represents only one possible interpretation of the behemoth's size. Because as we have seen, measuring these stars is uncertain. Their boundaries are unclear. Their structures are dynamic, which means that even this visualization may not fully capture the reality. The true behemoth, if it exists, could be different. Larger in some ways, smaller in others, more complex than anything we have imagined. This brings us back to the central question. If such a star can exist, even briefly, even in an unstable form, then what does that say about the limits of the universe? Are we looking at the upper boundary of what is possible, or just another step along the way? Because if a behemoth can replace a star like our Sun and completely redefine a solar system, then the implications go far beyond size. They challenge our understanding of structure, stability, and the very nature of stars themselves. At this point, the idea of a behemoth feels almost convincing. We've seen that the universe can produce stars of unimaginable size, stars that stretch across vast distances and challenge everything we thought we understood about scale. But there is a problem, a very serious problem. Stars this large are not supposed to exist, not for long, because the bigger a star becomes, the more unstable it gets. And eventually, that instability reaches a point where the star can no longer hold itself together. To understand why, we need to return to the balance that defines every star. Gravity pulls inward, trying to compress the star into a smaller, denser object. At the same time, energy produced in the core pushes outward, preventing collapse. This balance is what allows a star to exist in a stable state. But as a star grows larger, this balance becomes increasingly fragile. In smaller stars, gravity and pressure can maintain a steady equilibrium for billions of years. But in massive stars, everything intensifies. The core burns hotter, fusion reactions accelerate, and the amount of energy pushing outward increases dramatically. At first, this seems like it would support a larger size. More energy means more expansion. But this is where things begin to break down, because the outward pressure is not just balancing gravity anymore. It is fighting against it. And sometimes, it begins to win. When radiation pressure becomes strong enough, it starts pushing material away from the star. This creates powerful stellar winds, streams of particles moving at incredible speeds, carrying mass into space. These winds are not gentle. They can strip away enormous amounts of material over time. For the largest stars, this mass loss becomes extreme. The star is literally shedding itself, layer by layer. This creates a natural limit. No matter how much material a star begins with, it cannot hold on to all of it. The larger it becomes, the more violently it loses mass. This prevents the star from growing indefinitely and places an upper boundary on its size. But this is only the beginning of the instability. Another issue comes from the structure of the star itself. In smaller stars, energy moves from the core to the surface in relatively stable ways. But in giant stars, this process becomes chaotic. Convection currents, massive flows of hot material rising and cooler material sinking, can grow to enormous scales. Instead of small, consistent patterns, the entire star can be dominated by a few massive convection cells. This means that different regions of the star behave differently. Some areas expand while others contract. Some regions are hotter, others cooler. The result is a surface that is constantly shifting, never stable, always changing. For a star approaching behemoth size, this instability becomes extreme. The outer layers are no longer tightly bound. They are loosely held, almost drifting. It would not take much to disrupt them. Then there are pulsations. Many of the largest stars do not maintain a fixed size. Instead, they expand and contract over time. These pulsations can be relatively small, or they can be enormous, causing the star's radius to change dramatically. In some cases, the expansion becomes so extreme that the outer layers are pushed outward beyond the point where gravity can pull them back. When this happens, the star loses material in massive eruptions. These are not small events. They can eject vast amounts of gas into space, forming clouds that surround the star. Over time, this mass loss reshapes the star, reducing its size and altering its evolution. For a behemoth, this process would likely be unavoidable. It could reach an enormous size temporarily, but maintaining that size would be incredibly difficult. The star would constantly be fighting against itself. There is also the issue of energy. Larger stars burn through their fuel much faster than smaller ones. The rate of fusion increases dramatically with mass, meaning that the most massive stars have the shortest lifespans. While a star like the Sun can exist for billions of years, a massive giant may only last a few million, and during that time, it evolves rapidly. Its structure changes, its size fluctuates, its stability decreases. This means that even if a behemoth exists, it may not exist for long. It could be a fleeting phase, a moment in the life of a star that is almost impossible to catch. And then there is the ultimate limit: gravity. If a star becomes too massive, its own gravity may eventually overwhelm all other forces. The outward pressure from fusion can only do so much. Beyond a certain point, it cannot support the weight of the star. When this happens, collapse becomes inevitable. The core may implode, leading to a supernova explosion. Or, if the mass is high enough, the star could collapse directly into a black hole. This sets a hard boundary, a point beyond which stars cannot exist in their current form. So the idea of a behemoth must exist within these limits. It cannot be infinitely large. It cannot be perfectly stable. It must exist in a narrow range where expansion is possible. But collapse has not yet occurred. This creates a paradox. The larger the star becomes, the closer it gets to destruction. The very factors that allow it to grow also make it unstable. So a true behemoth, if it exists, would not be a calm, stable giant. It would be a chaotic, evolving object, constantly changing, constantly losing mass, constantly on the edge of collapse. This raises an important question. If stars this large are so unstable, why do we see them at all? The answer lies in timing. We are observing them at specific moments in their evolution. Moments when they have expanded to extreme sizes, but have not yet collapsed or shed enough mass to shrink again. These moments may be brief on cosmic timescales. But because the universe contains so many stars, we are able to observe some of them in this phase. It is like taking a snapshot of something that is constantly changing. We catch it at just the right time. For a behemoth, this timing becomes even more critical. If it represents the upper limit of stellar size, then its existence may be extremely short-lived. It may expand to its maximum size only briefly before instability forces it to change. This makes it incredibly difficult to confirm, because by the time we observe it again, it may no longer be the same. All of this leads to a deeper realization. The largest stars in the universe are not stable records. They are temporary extremes. They represent moments where conditions align to create something extraordinary, but those conditions cannot last. This means that the title of largest star is not fixed. It is constantly changing, passed from one object to another as stars evolve, expand, and collapse. And this brings us back to the behemoth. If such a star exists, it would not be a permanent giant ruling over the universe. It would be a fleeting phenomenon, a brief expression of what is possible at the edge of physics. A star that exists not in stability, but in transition. By now, the idea of a behemoth feels both possible and uncertain at the same time. We've seen that stars can grow to unimaginable sizes, that some push the limits of physics, and that instability makes these giants temporary and difficult to study. But all of this leads to one unavoidable question. What if the behemoth isn't real at all? What if the largest star we think exists is not actually as large as we believe? This is where science becomes both careful and skeptical. Because in astronomy, especially at extreme scales, not everything we observe is exactly what it appears to be. The universe does not always present itself clearly. Light travels vast distances, passing through clouds of gas, bending around massive objects, and interacting with environments that can distort what we see. By the time that light reaches us, it carries information. But it can also carry illusions. One of the biggest challenges comes from distance itself. The stars we are discussing are not nearby. They are thousands, sometimes tens of thousands of light years away. At these distances, even the most powerful telescopes cannot resolve fine details. Instead of seeing a clear image, we detect a point of light and analyze its properties. From that single point, we try to reconstruct an entire star. Its temperature, its brightness, its size, its structure. But this reconstruction depends on models, and those models depend on assumptions. If any of those assumptions are slightly incorrect, the final result can be dramatically different. A small error in distance can lead to a massive error in size. A star that appears to be the largest known could suddenly shrink if its distance is recalculated. Or it could grow even larger if we discover it is farther away than expected. This means that some candidates for the behemoth may not actually be as large as they seem. Another source of uncertainty is the star's environment. Many of the largest stars are surrounded by thick envelopes of gas and dust. These envelopes are often created by the star itself as it loses mass over time. When we observe such a star, we are not always seeing a clean, isolated object. We are seeing a complex system. Light from the star interacts with the surrounding material, scattering and spreading in ways that can make the object appear larger. In some cases, what we interpret as the edge of the star may actually be part of this extended environment. This creates a kind of visual ambiguity. Where does the star end? Where does the surrounding cloud begin? The answer is not always clear. And depending on how we interpret that boundary, the size of the star can change significantly. There is also the possibility of misidentification. In crowded regions of space, multiple stars can appear very close together from our perspective. Their light can blend, creating the illusion of a single, larger object. Without careful analysis, this can lead to overestimates of size and brightness. In some cases, What appears to be a single massive star could actually be a group of stars, or a binary system where two stars orbit each other so closely that their light merges. These scenarios can complicate measurements and lead to incorrect conclusions. Variability adds another layer of complexity. As we've seen, many giant stars are not stable. They expand and contract over time, sometimes dramatically. This means that their size is not constant. A measurement taken at one moment may not represent the star's typical state. If a star is observed during a period of maximum expansion, it may appear larger than it usually is. If that measurement is taken as its defining size, it could be classified as one of the largest stars, even if it spends most of its time in a smaller state. This raises an important question. What does it mean for a star to be the largest? Is it the largest it has ever been, or the largest it typically is? The answer is not straightforward. Despite all these uncertainties, it would be a mistake to dismiss the idea of the behemoth entirely. Because even when measurements are refined, even when errors are corrected, we are still left with stars that are incredibly large. The exact numbers may change, but the existence of extreme giants is undeniable. The question is not whether large stars exist. The question is how large they can truly be, and whether any of them reach the level we imagine when we think of a behemoth. There is also an important point about how science evolves. When something challenges our expectations, the first response is often skepticism. Scientists question the data, recheck the measurements, and look for alternative explanations. This is not because they want to dismiss new ideas, but because they want to ensure that those ideas are correct. Over time, as more data becomes available, the picture becomes clearer. Some candidates are ruled out, others are confirmed, and occasionally, something unexpected remains, something that cannot be easily explained. It is in these moments that new discoveries are made. The behemoth, whether it exists as a specific star or not, represents one of these moments. It is a question at the edge of our understanding, a possibility that forces us to examine our methods, refine our models, and push our observations further. Even if no single star holds the title definitively, the search itself reveals something important. That the universe is more complex than we assume, that our measurements are limited, and that there may always be something just beyond our reach. There is also the possibility that the true behemoth is hidden, not because it is invisible, but because we have not recognized it yet. It could exist in a distant region of space, its light still traveling toward us. Or it could be obscured by dense clouds of dust, undetectable with current instruments. It might even be something we have already observed, but misinterpreted. A star whose true size has not yet been fully understood. This possibility keeps the search alive, because it means the answer may already be out there, waiting to be discovered. So is the behemoth real? The honest answer is, we don't know. There may be stars that approach this extreme. There may be candidates that come close, but confirming a true behemoth, something that clearly exceeds all others, remains one of the most difficult challenges in astronomy. And yet, the uncertainty does not diminish the idea. It enhances it, because it reminds us that we are still exploring, still learning, still uncovering the limits of what the universe can create. After everything we've explored, the birth of stars, the limits of their size, the giants we already know, the mystery of the behemoth, and the uncertainty in how we measure the universe, we arrive at the question that started it all. Is this the largest star in the universe? It feels like a question that should have a clear answer, a number, a name, a final record that stands above all others. But the deeper we go, the more that certainty begins to disappear. Because the truth is far more complex. The universe does not organize itself around our need for simple answers. It does not label its extremes or present them in neat categories. Instead, it exists in constant motion, expanding, evolving, and changing in ways that make fixed definitions difficult. And nowhere is that more evident than in the search for the largest star. What we call the largest star today is based on the best data we have right now. It is an estimate built from observations, refined by models, and supported by evidence. But it is not absolute. It can change. New observations can revise distances. Improved instruments can reveal hidden details. Better models can reinterpret what we thought we understood. A star that holds the record today may lose it tomorrow. And something we have not even noticed yet may take its place. The idea of the behemoth captures this uncertainty perfectly. It represents not just a single star, but the possibility that the limits of size are still unknown. That somewhere in the universe there may exist something larger than anything we have confirmed. Or perhaps many such stars, hidden in distant galaxies, obscured by dust, or simply too far away for us to measure clearly. Because when we look into space, we are not seeing everything. We are seeing a fraction, a small window into something far greater. There is also the question of limits. Physics suggests that there should be boundaries, that stars cannot grow indefinitely, that instability and mass loss will eventually prevent further expansion. But these limits are not always precise. They depend on conditions, environments, and factors we may not fully understand. And sometimes, nature finds ways to approach those limits in unexpected ways, pushing right up against them, or appearing to cross them, even if only briefly. This is what makes the search for the largest star so compelling. Because it is not just about size, it is about testing the boundaries of what is possible. And then there is time. The universe is not static. Stars are born, evolve, and die. The largest stars we see today may not have existed in the past, and new ones may form in the future. A behemoth, if it exists, may only appear for a brief moment in cosmic history, a phase so short that it is incredibly difficult to observe. This means that even if the largest star does exist, we may never see it at its peak. We may only see hints, fragments, moments captured out of a much larger process. And all of this leads to a surprising conclusion. The question, what is the largest star, may not have a permanent answer. It may always be changing, always evolving, always just beyond complete certainty. And that is not a limitation. It is a reflection of the universe itself. Because the universe is not built to give us final answers. It is built to be explored. Every discovery leads to new questions. Every answer reveals new mysteries. And the deeper we go, the more we realize how much remains unknown. The behemoth, whether it is a real star or simply an idea, represents that boundary, the edge of what we understand, the point where knowledge begins to fade into possibility. It reminds us that even in an age of advanced technology and deep observation, there are still things we cannot fully grasp, still extremes we cannot fully define, still mysteries waiting in the darkness. So is the behemoth the largest star in the universe? Maybe. Or maybe it is just one of many. Or maybe something even larger exists, far beyond our current reach. And that is where the story truly ends. Not with a final answer, but with a realization that the universe is far bigger, far stranger, and far more mysterious than any single discovery can explain.